Hi everyone, welcome to this meeting. Thanks for joining. We'll get started properly in a few minutes' time once a few more people have had a chance to join. Hi everyone, thank you for joining. I think we're going to get started quite promptly and get going because we've got a lot we want to cover today. I know a few more people will be joining, but we'll just get through our introductory slides. So welcome everyone to this webinar on the draining of the Fens. This webinar is being brought to you by the British Hydrological Society South East and East Regional Group, which we launched last year. I'm Claire Waller. I'm a senior advisor in the National Flood Hydrology team at the Environment Agency, and I'll be chairing today's call. And we also have Lisa Chatterjee here, who's also on our committee, and she'll be helping me with the Q&A. So just a little bit more about the BHS South East and East group. So the co-chairs are Tracy Haxton and myself. Our aim is to arrange meetings and events online and in person. We focus on the hydrology of the South East and East region of the UK. If you'd be interested in helping organise events or have any ideas about events, please do get in touch. Our committee email address is on the screen. The image on the right of that slide is from the BHS website. It's just been updated in the past few days. If you haven't visited recently, please do take a look. It's really great work done by the BHS committee to update that. The web address is shown on that slide. It's hydrology.org.uk. And there you can also find information about some other upcoming events. So there is a peak flow data meeting in person in Scotland in June. We have a national meeting on drought hydrology in London, also in June. There's the Peter Wolf Early Careers Symposium being held in London in June. And then the National Symposium is coming up in September in Leeds. So a few housekeeping notes. Please do keep yourself muted and your video turned off during the presentations. This meeting is being recorded and it will be shared on the BHS YouTube channel in due course. The chat is disabled, so if you have questions, please write them in the Q&A box, which you can find on the top bar next to the chat in Teams. We'll go through the questions at the end of the talks, and you can also upvote other questions in the Q&A. So if there are lots of questions, we'll take the most highly voted ones to start with. And please do keep your questions relevant to the topic of this webinar. So I'd like to thank today's speakers for giving us their time for this webinar, and I'll just briefly introduce them before handing over to them. So we have Sean Faulkner. Sean is a chartered civil engineer and senior associate at Stantec with over 10 years experience specialising in lowland drainage and coastal management schemes. He oversees projects from conception and business case production through to consenting, detailed design and construction. We also have Yvonne. Yvonne is a senior flood risk consultant at Stantec with 5 years experience of flood risk management and water resources. Her technical experience includes infrastructure engineering for land development and planning with a focus on flood risk assessments, drainage strategies, environmental impact assessments, peatland restoration and water resource planning. And then we also have Max. Max is a principal flood risk consultant at Stantec with over 6 years experience in hydraulic modelling, hydrology and flood risk management. He specialises in pumped catchments, outline business cases and economic appraisals for major infrastructure projects. So, Sean, over to you. I'll stop sharing my screen and hopefully you can share yours.
Thank you. Here we go.
Yeah, we can see that. Thanks.
Let's go start. Okay. So if you haven't heard of us, Stantec are a global consultant in sustainable engineering, architecture and environmental consulting. And we've offices throughout the world, including the UK and Ireland. I'll start the talk today with some historical context around lowland drainage in the Fens, specifically the 17th century drainage projects that have created the current landscape. Max will then discuss hydrology and hydraulic modelling, and Yvonne will finish with a review of the impact on peatlands and restoration schemes that aim to address that. So when we talk about the Fens in the context of this presentation, we're referring to the low-lying areas around the east coast of England, shown here in purple on the topo plan. Prior to the drainage schemes of the 17th century, the Fens were generally at or a bit below mean sea level. So some parts would generally have been flooded all year round, other parts would be flooded in the winter, but then dry generally in the summer. And then other areas would be dry all year round, and that's where settlements, such as the Isle of Ely, for example, would have formed and established. The watercourses provided a decent economy to the people of the Fens, provided an abundance of fish, eel, waterfowl, and then the land in the summer provided great land for pasture, because the winter flooding would enrich it. You could also have polluted culture and other purposes like that. Just removing the topo, the areas shown brown here are peatland. Yvonne will discuss this further later, but in simple terms, peat is formed from the decomposition of organic material over a very long period of time. And a key requirement for that formation is fresh water. So the freshwater wetlands is where those peat areas would have formed, and then the more saline coastal wetlands is where marshlands would have formed. Technically, the Fens refers to, or fenlands are characterised by peat, but when we say the Fens, we're referring to the entire area. Bear in mind also that this is a modern day map, so peat extents back pre-17th century likely have been a lot more extensive than that. So how did the draining of the Fens come about? Up until around the 17th century, the inhabitants of the Fens tended to work with the natural environment, didn't really make major changes to the drainage regime. They maintained it, tried to control flooding to an extent. A large portion of it was owned by the Catholic monasteries up until around the middle of the 16th century, when King James I dissolved the monasteries, and all that land was subsequently sold on to wealthy landowners, predominantly located outside the Fens. So they didn't really have the same understanding of it. They didn't understand how to maintain it. They weren't really complying with the commissions of sewers, which would have been basically the internal drainage boards of the day. So there was a bit of a conflict there, and generally they were more interested in the idea of draining it, thereby increasing their land holdings. So they would have arranged for various surveyors to go out, survey the lands and consider the feasibility of draining it. And invariably they came back suggesting that it was very much doable, and indeed wouldn't have been that difficult or that expensive. Other landowners that were, there for a longer period of time were generally not in favour of such a scheme. They felt it was unrealistic. They were already making a decent living, and And the biggest stumbling block would have been that they would need to contribute some of their land to fund such a scheme, which, as I said, they believe wouldn't really be feasible in the first place. This was all at a fairly politically unstable time, as you can see here, with civil wars obviously having a major impact, changes of the ruling class, etc. Without going into too much detail in the time we have today, the first drainage scheme, which was the Hatfield level, was pushed through by King Charles I. He then moved on to the Great Level, which was postponed during the civil wars, but then recommenced and completed during the interregnum period under Cromwell. So the Hatfield Level scheme, Hatfield Level is an area of about 28,000 hectares in North Lincolnshire. As you can see here, discharges to the Humber Estuary. King Charles owned a lot of that land at the time, so he felt it'd be easier to push through, and abused his prerogative powers to do so. He appointed Dutch engineer Cornelius Vermeulen to come up with a scheme to drain it, and that scheme, in simple terms, involved redirecting the existing main rivers, so creating more direct routes to the sea. In doing so, you could achieve a steeper gradient, therefore higher flow velocity, and in addition to getting the water away more quickly, it was hoped, clear silt as well, which was a problem at the time. In addition to that, Vermeulen had a design principle which involved creating a raised bank set back from the existing channels. The idea of that was to have an upper flood storage area for exceedance events. If I go to the next slide, you can see here some of the main works. This was also applied on a smaller scale, which isn't really illustrated on this plan, but those were the main principles behind the scheme, really. Bearing in mind there wasn't really theoretical design at the time or much experience to go on either. One of the issues on this project was for the River Don and the River Idle, which were two of the main rivers. Vermeulen only constructed those raised banks on the side of the drains that he was protecting or being paid to protect. So water just overflowed on the other side, flooded a whole new area, created new problems. And initially he resisted sorting that out, but eventually, after spending a short term in prison, he was convinced or incentivized to resolve it. But ultimately, the scheme proved just how difficult draining the Fens would be. And Vermeulen lost a lot of credibility because the budget was massively overblown. All his backers, financial backers, lost a lot of money on it. And then when it came to the Great Level, which was a lot more ambitious, about 120,000 hectares, he didn't really have the backing to deliver that. So instead, the Earl of Bedford initially carried out a project. He identified financial backers and delivered a scheme which was aimed mainly at keeping the Fens dry in the summer, so more consistently and more reliably, but accepting that parts of it would still flood in the winter. That was initially accepted by the king, but soon after it was completed, it was decided that it wasn't good enough. So Vermeulen was brought back in to work his magic. The king gave him the financial backing to get around that problem, and he progressed with this scheme. Again, just highlighting the key systems that were in place. You can see the centerpiece of the initial scheme by the Earl of Bedford was what is now known as the Old Bedford River. So that was designed to realign the River Great Ouse, create a more direct route to sea with more capacity. When Vermeulen took over, he felt that wasn't adequate. So he constructed the New Bedford River, which is parallel with a significant chunk of land in between. And again, he built those raised banks offset, but he did it on the outside of each river, creating a large storage area in between, which was a pretty good idea. Also put in a large a large sluice gate at the upstream end. So that was to divert the great river ooze to these new rivers. And there was a large sluice also installed downstream as a tidal gate. Some of these structures at the time would have been major feats of engineering, and given that there wasn't really any major heavy machinery to use, it would have been a massive undertaking. So the work required thousands of men painstakingly digging out and transporting muddy, peaty soil to create these channels. And at its peak, it's estimated that about 10,000 men were employed and millions of cubic meters of soil had to be moved. Bermuda initially estimated that the project would cost about 120,000. It's obviously quite a lot back then, but it turned out to be more like 300,000, and that's not to mention the vastly underestimated cost to maintain the new drainage regime that they'd created in the years ahead. Several issues arose quite quickly. Firstly, as we know now, drain and peat causes it to shrink and the associated land to settle. This was accelerated further by ploughing the land for agricultural purposes. It was found that land was settling by a few inches a year, and before long, parts of the drained land had dropped below mean sea level. So whereas previously you could potentially drain at certain times of the year by gravity, that was no longer feasible. And the land was now lower in relation to the drains that it was to discharge to. So that became a new problem as well. With regards to these new drains and rivers, the riverbanks were constructed using locally available soils, which of course is peat generally. Probably the worst type of soil you could use for that purpose. So they needed to be constantly rebuilt. In the years since, clay puddling became a thing, and that problem was eventually resolved. But yeah, there was the main issue was the settlement of the drained land relative to the drains of the sea. As a result of that, wind pumps proliferated the landscape, started popping up everywhere. There's an image there to the left which shows what the earliest versions would look like. So wind-driven scoop wheels. They are as rudimentary as they look in that image. They're limited in terms of the lift height they can provide. So in many cases, you would need a number of these in series to achieve the required lift height. Also, they're wind-driven, so only work if the wind is blowing, which is a major constraint. And then over time, things obviously improved technology. It's worth noting, as indicated on the top of that timeline, the draining of the Hatfield level and the Great level was based on empirical, experience-based design, although there was a lack of experience even in that case, rather than modern theory-led design, as Max will discuss later, which didn't really become dominant until the early 19th century. It was also pre-industrial revolution, so as mentioned, they were poorly equipped to deliver such a scheme. But in the years since, obviously, there's been a lot of technological improvements. In 1934, St. Germans pumping station was constructed. That initially had a capacity of 40 cumex, 40 meters cubed per second. It's been upgraded over the years. Currently, it's got a total capacity of about 100 cumex, which supposedly can drain an Olympic swimming pool in 25 seconds. But that further highlights just how difficult such a drainage scheme would have been in the 17th century. Other impacts, so a major impact of the scheme was loss of wetlands and their associated habitat, as well as the impact on peat, which Yvonne will discuss later. The image here is of the Ouse Washes, which is 20 miles long. That's that stretch of land between the Old Bedford River on one side and the New Bedford River on the other. Like parts of the pre-drained fens, it floods in the winter, providing great ecological value, great source of habitat to a diverse range of species. And then in the summer, it can provide really good land for pasture. So potentially a glimpse into what certain parts of the fens would have looked like, but obviously were underappreciated at the time. And then you've got Wicken Fen. So unlike the Ouse Washes, which was engineered as part of those drainage projects, Wicken Fen was naturally left untouched. And according to the National Trust, it is the first nature reserve in the country to record over 10,000 species. So again, another side of huge environmental value. But again, something that was underappreciated at the time, unfortunately. So pass you over to Max to bring us up to modern day.
Yeah, thanks, Sean. So yeah, I'm Max Davison. I'm going to take you through the hydrology and hydraulic modelling side of fenland management. As Sean has mentioned, yeah, he talked about the historical context, and I'm going to bring up to present day. So we'll cover who is responsible for managing the risk today, how we approach catchment scale flood studies, the unique hydrology challenges that fenland catchments present, and how we tackle those challenges in practice. And then I'll finish up with a live project example as well. So starting off with who is responsible for keeping all of this drained today. There's two key organisations that share responsibility. So there's the internal drainage boards, the IDBs, and they are local public authorities with statutory responsibility for managing water levels and lowland drainage. The map on the slide shows the various IDBs that manage water levels, and naturally many of those are concentrated in the eastern areas of England. There's also the Environment Agency, who sit above the IDBs, and they're responsible for flood risk from main rivers, reservoirs, estuaries, and the sea. In practice, the two work closely together, particularly for the large catchments. In terms of what's at stake, the scale of what they're protecting it's generally remarkable. So we're talking about 600,000 people, close to 1 million properties, 50,000 farms or land holdings, significant amounts of critical infrastructure like power stations and transport routes, as well as Sean mentioned, designated sites like SSSIs. This isn't just agricultural flat land, it holds critical natural infrastructure, and the drainage systems underpinning it require constant informed management. Next slide, please. So focusing on the IDBs themselves, so more than half of all IDB managed land, which is over 635,000 hectares, relies entirely on pumping to stay drained. Gravity simply isn't an option across much of the Fens. The network is formed of around 22,000 kilometres of watercourses and roughly 500 pumping stations. The annual spend of around £100 million is just to keep it all functioning. There's two significant challenges to these systems at the minute. So the first is many of the assets are aging. So a lot of these pumping stations were built in the 1950s and 60s, like Sean mentioned, and they're approaching the end of life. Secondly, climate change. It's intensifying pressures on the system through more intense rainfall events, sea level rise, and shifting seasonal patterns. So that's why informed catchment studies underpinned by hydrology and hydraulic modelling are essential. You need to properly understand the system before you can make the right decisions on how to manage and invest in it. Next slide, please. What do we mean by a catchment study? So a catchment study provides an overview of the system, how water moves through a landscape, from rainfall all the way through to flood risk at a property or to a catchment level. So in practical terms, they deliver three things. First, an evidence base grounded in topographical, hydrological and hydraulic data, giving you a defensible picture of flood risk as it exists today. Second, a validated hydraulic model of baseline flood behaviour, mapping flood depths, extents and velocities across a range of storm events. And thirdly, often the most valuable part for IDBs is a framework for testing potential interventions before any money is committed to the ground. So you can simulate a new pumping station, storage basin, changes to operational levels, and see how that difference makes across the system. Process diagram on the right shows how each stage feeds into the next. Next slide, please, Sean. So before I get stuck into how we approach hydrology, it's worth spending a moment on why fenland catchments are so different, because this shapes everything that follows. Fenland and pumped catchments behave differently to typical grain-drained catchments, and so the standard UK hydrology methods don't always account for this. Reasons being artificial drainage control alters the natural rainfall runoff response. The groundwater dominance and extremely flat terrain can affect how flow behavior, in many standard models, they don't really account for that properly. And lastly, the storage effects, tidal influences, and the pumped controlled boundaries, they add further complexities that need to be accounted for. An important point here is that fenland catchments, the flood hazard within them is driven more by the volume of runoff over time instead of the peak discharge rates. And this has significant implications for how we select and apply hydrology methods. The flood estimation guidelines, which were updated last year, it does provide some key information and guidance, which can be applied to these more unusual catchments. Next slide, please. So building on that, there are 4 specific areas that require particular care in fenland catchments. The first being how the catchment is delineated. So in a typical catchment, you'd probably draw the boundary based on topography using a digital elevation model. In the Fens, boundaries follow mostly the drainage ditch connectivity rather than topography. So getting this right requires IDB mapping, historical studies, engineering judgment, and often site walkovers to get it correct. You also have to think about flow complexity. The flow direction in these systems can reverse under changing hydraulic gradients, so controlled by pumps or tidal conditions, and standard models won't capture this without very careful setup. There's also soil and drainage effects, so standard soil classifications can underestimate runoff in permeable lowland catchments, and shallow groundwater tables with dense field drainage networks aren't fully represented by standard parameters. Then finally, the FEH statistical approach, including its QMed derivation, excludes pumped catchments within this. So for these types of areas and catchments, it should generally be avoided. Next slide, please. So how do we actually approach hydrology in practice? So the preferred method or approach is rainfall runoff modeling, using RefH2 as a starting point, ideally coupled with a water balance assessment to ground the results and what we're observing in the catchment itself. So the water balance adjustment works by using pumping records and observed catchment inputs and losses to estimate a target runoff volume that could be realistically contributing to flooding. You can then iteratively adjust the BFI host 19 catchment descriptor until the modeled runoff aligns with this target. What we're effectively doing is artificially representing the conditions of a pumped or fenland catchment, so the reduced infiltration capacity or the high groundwater levels. This is usually done on a catchment scale, so for a lumped catchment, and then the outputs of the assessment could be area weighted for any subcatchments. So the catchment on the right on your screen shows an example of a subcatchment delineation for this type of system or a fenland catchment. Next slide, please. Where the adjusted RefH2 approach isn't available, possibly because there's a lack of pumping data that you can use or climate or input data that you can find, there are alternatives worth knowing about. So one of them is Samuel's method, which applies a trapezoidal unit hydrograph to represent the catchment response, illustrated on the right. It can be useful as a cross-check or a fallback method, but there's an important consideration worth knowing due to how it treats the unit hydrograph by effectively removing the peak of it. There's a risk of double counting attenuation if the Samuel's method is combined with other routing or storage assumptions elsewhere in the modeling. So this is a key limitation of that method, so it needs to be applied quite carefully. An alternative approach could be just using a standard RefH2 or rainfall runoff method without the water balance adjustment. This still may provide sufficient estimates of flows, particularly for winter design storms. But with any hydrological method, they should all be applied with consideration for engineering judgment, and results should always be sense checked against any available data. Next slide, please. So moving on to hydraulic modelling, pumped Fenland systems do require quite careful schematization of the drainage networks with detailed representation of the operational assets, structures and controls, such as the pumps, sluices, tidal flaps or weirs. Some of you may know there's broadly 3 modelling approaches that you can take. So 1D only models that represent in-channel areas only are more suitable for heavily engineered systems where out-of-bank flow is limited. They're simpler to build, but obviously unable to represent floodplain flow paths. And on the flip side of that, 2D only models can represent overland and floodplain flows across a computational grid without explicitly representing individual channels. Those are more useful for where surface water flooding is primary concern, but it's obviously limited in detail for the in-channel hydraulics. The combination of the two through 1D, 2D modeling, where you can couple explicit channel representation with 2D floodplain routing, is usually the preferred approach for these types of Fenland catchments, because the interaction between the drainage network and the surrounding low-lying land is quite important to understand. I've listed 2 commonly used software platforms on the slide in the UK, so that's Flood Modeler from Jacobs or 2Flow from BMT Group. Next slide, please. So once a validated hydraulic model is in place, it can be used to simulate quite a wide range of scenarios and events. In a typical study, you might cover 3 scenario types. So you'd obviously have a baseline representing the existing catchment conditions. You might have other ones such as testing any interventions you might want in the catchment. So that could be new assets, increased storage, channels, natural flood management measures potentially, and any changes to operating levels. And then lastly, you might do sensitivity testing to understand how results change with different assumptions on aspects like surface roughness, structural blockages, or downstream boundary conditions, whether they be fluvial or tidal. And then in terms of modeling specific storm events, the full range can be simulated. So from very frequent lower magnitude floods like the 1 in 2 year events, right through to more extreme events like the 1 in 1,000 year. Crucially, we can model both present day and future conditions. So typically looking at the 2050s and 2080s for the future scenarios. And these are typically using UK CP18 climate change projections across a range of emission scenarios. Next slide, please. It is worth mentioning that a model is a simplified representation of reality, not reality itself, and that the results from them should only inform and support engineering judgment. They should never replace it. So in general terms, all models carry inherent uncertainty and are only as good as their input data. Hydrology is usually the biggest source of uncertainty, typically due to limited observed or gauged data, which makes verification of any of their outputs quite difficult. And then on the hydraulic modeling side, data quality can influence the confidence in outputs. There's also how the pumps are represented, might require some assumptions that may not perfectly reflect the real world behavior of these assets. And then obviously you have to simplify a very complex drainage network, which may involve some trade-offs. However, it should be noted that none of this undermines the value of the modeling. The studies and their output should always be transparent about the uncertainties within it and use the results as one way to inform decision making. Next slide, please. So pulling this all together, why does it matter? On the flood risk side, good catchment modeling can establish where flood risk is greatest and why, can map flood behavior across a range of events and scenarios, and identifies where action will have the greatest impact, while also helping to avoid unintended consequences elsewhere in the catchment. And that last point is particularly important in Fenland catchments due to how interconnected they all are together. On the decisions and investment side of it, modeling lets you test potential interventions before committing money to the ground, can support option appraisals, economic damage assessments, and both those can underpin outline business cases for FCRM grant and aid funding, which is usually the primary route through which IDBs can access government investment for asset refurbishment, replacement, or construction. I should flag that the FCRM project's funding guidance and policy is currently being updated, so it's worth keeping an eye on any developments in that space. The example of the right is from Wrangle pumping station. So the catchment study for that and the related OBC, the IDB were able to secure funding to construct a new replacement pumping station. So the pictures just show the project going through from construction phases towards the top of the screen down to the completed pumping station at the bottom. Next slide, please. To finish off with a live project example, I wanted to share the Hop Hole pumping station project, which is located in Lincolnshire near Boston. Managed by Witham Forth IDB, Hop Hole is a critical part of the Witham East and West Fens flood defence system. It protects a large low-lying agricultural and residential catchment where the effective water level management is key. The existing infrastructure, which you can see on screen, consists of a diesel pumping station, which was originally built in the 1950s, and an additional electric station was constructed in the 1980s, which you might be able to see just to the left of the main structure. However, the assets are reaching the end of life, and the case for replacement is straightforward. This is quite an essential flood risk management asset, and there's no other alternative drainage mechanism for the catchment. Without it, the catchment would essentially just fill up with water and flood over time. So the aging infrastructure is giving a increased risk to long-term resilience, and with climate change predicted to intensify flood risk across the catchment, future-proof replacement is required. Next slide, please. The modelling work for Hop Hole applied the adjusted RefH2 hydrology method to account for the pumped nature of that Fenland catchment condition, and an estuary 2 flow 1D 2D hydraulic model was used to represent drainage work and key structures. Multiple scenarios and catchment interventions were simulated to test options and understand how flood risk changes under these different conditions and future climates. What the modelling is delivering in practice is a direct evidence base comparing the potential options for replacing the station. Also the technical foundation for an emergent outline business case in order to try and get FCRM grant and aid funding. It's also providing a clear demonstration of the long-term benefits of investing in a modern pumping station. Currently, the preferred option is a future-proof replacement. This will be utilising efficient pumps to provide a low-carbon and resilient system with improved environmental performance by having the pumps be efficient friendly. Ultimately, the new station will provide long-term protection for local communities, agriculture, and the critical infrastructure across the catchment. I'll now hand over to Yvonne, who will take us through the peatland restoration side of the story. Thank you.
Thank you, Max. Yeah, I'll now talk about lowland peatland degradation and restoration, as well as an example of restoration within the Fens. Next slide, please. So to start, peatland formation, it's the result of incomplete decomposition of organic matter, such as the remains of plants formed in waterlogged conditions. This typically occurs in standing water, such as in lakes or along margins of very slow flowing rivers, or it can form in areas with consistently high rainfall, such as upland or mountain regions. And because this decomposition is incomplete, plant remains gradually accumulate and compact over time, forming the peat. It's a very slow process. It accumulates around 1 millimetre per year, so it does take around 1,000 years just for 1 metre to form. In a hydrological context, peatlands are commonly divided into 2 basic types. We've got ombrotrophic, fed by precipitation only. This creates nutrient-poor, acidic peatlands, as there's no contact with the groundwater, and these are classically called bogs. And we've got minerotrophic, which are fed by both precipitation and the groundwater. In contrast, these are fairly nutrient-rich, as the water's been in contact with bedrocks or soils. We've quite a variety across the UK, where there's ombrotrophic blanket bogs formed in the uplands. The drainage is poor, rainfall exceeds evapotranspiration. These are found across Scotland, where we've got extensive carpets of blanket bogs. And then we've got another type. These are fens, these minerotrophic, waterlogged lowland peatlands. Next slide, please. So, as Sean has discussed, the fen and peat first formed across a wetland landscape. This was caused by rising sea levels and climate change following the end of the last ice age 10,000 years ago. The rising sea levels created a sort of slow-moving swathe of water across the land, formed shallow lakes, which had poor drainage. But there's a constant inflow of water causing these waterlogged conditions. And within shallow basins, fen and peat began to form. So the fenlands of East Anglia are the largest area of these Holocene deposits in Britain. And up until the large-scale drainage began in the 17th century, the fens formed a vast and continuous wetland landscape. The fen appearance is driven by both the nutrient content and the acidity of water, but they do typically form flat, open landscapes with dense vegetation, intersected by streams, ponds, and some transitional habitats, such as like wet woodlands or raised bogs, if left undisturbed over time. And depending on the underlying geology, the groundwater feeding the fens can be mineral rich, supporting quite dense vegetation. And contact with the groundwater makes fens less acidic than bogs. So this nutrient-rich fen peat that's formed across the fenlands has created some of the most valuable crop-growing regions in the UK. Sometimes it's referred to as the breadbasket of England. Next slide, please. Healthy peatlands are among the most carbon-rich ecosystems on Earth. They do store vast quantities of carbon. It's because a healthy peatland captures CO2 from the atmosphere through photosynthesis of the plants that grow across a peatland. And under waterlogged conditions, the dead plant material doesn't fully decompose, and the carbon is locked into the peat and is prevented from being released back into the atmosphere. Further to this, we've got some other examples on the screen. So they can reduce flood risk by slowing that flow of water and providing an area of storage, and also supporting unique biodiversity. Blanket bogs are sometimes referred to as rainforests of the UK due to their ecological importance and rarity, which I quite like. Next slide, please. Unfortunately, the majority of UK peatlands have been historically managed in a way that have left them damaged and in need of urgent action. They're degraded due to human interventions, including pollution, artificial drainage, burning, and livestock grazing, to name a few. So across the fens, peat cutting occurred from at least the 12th century until around the early 20th century. And further to that, it was this large-scale drainage, which did begin in the 17th century. Following this drainage, the fen and peat lost the water, which creates the bulk of the peat, and in turn, that peat contracts and subsides. So subsidence is a huge problem in this area of the UK. And as shown on the previous slide, whilst it takes 1,000 years for a metre of peat to build up, drainage does mean that the land surface can reduce on average 1 to 2 centimetres per year through subsidence due to peat oxidation. So that's 10 to 20 times faster than it's accumulating. So that means for large areas of lowland peat in the fens that it's now below sea level and at risk of flooding. Peatland drainage can also cause soils to dry out and erode easily. The peat can shrink and decompose further, and it can be washed away or literally blown away in the wind. And that does create a cycle where, as further peat's lost, the drained soil is reduced. The drains have to be dug deeper to keep surrounding crops from being waterlogged, causing further drainage, and on it goes. So in some areas of the fens, the peat has disappeared completely and it's just left the clay underneath. Another huge issue is when peatlands are drained, they become oxygenated and air causes the peat to dry out and begin to decay. So this turns the carbon that was once stored within the peat to turn it back into carbon dioxide. So they can go from being a carbon sink to a carbon source, and that releases into the atmosphere centuries worth of stored carbon. And the balance of whether a peatland is a carbon store or emitting carbon does depend on the peatland's condition. Next slide, please. not all doom and gloom. So across the UK, peatland restoration is being led by government bodies, NGOs, landowners, private sector, and like water companies. So peatland restoration measures are highly dependent on the type of peatland, but to restore degraded lowland peatland, like we have in the Fens, raising the water table in the drained areas is required to create these waterlogged conditions, which in turn reduces the oxygen availability and results in this partial decay of plant materials, which generates peat formation. So a suitable water level management strategy to raise the water table close to the ground level surface is key. Ideally, that's between 10 to 30 centimetres as a bit of a standard, but this needs to be achieved year round, ideally, as fluctuations in the water table results in sort of intermittent wetting cycles, which can be damaging. Strategies can involve blocking drainage ditches, adjusting the existing management systems, and removing non-native trees. But it's absolutely key to have a sufficient and reliable source of licensable water available all year round. It must be identified how water moves around the site and ensuring the depth is sufficient. But if there isn't any water available, then it's not going to be successful. So to support successful peatland restoration, often a catchment assessment, hydrology modelling, optioneering assessments, and gaining the suite of permits, permissions, licenses is required. It's also useful to have a good understanding of the underlying geology to inform engineered solutions like types of sluices or whether a wind pump is required to lift water over raised carrier drains. Next slide, please. I can't talk about fen and peat without mentioning the home fen post. So home fen is one of the last remaining fragments of ancient East Anglian fenland. It's associated with the Whittlesea Mere. And in the 1840s, a group of local landowners agreed to drain Whittlesea Mere and take their share of the drain land. It was anticipated that the peatland might shrink as the area was drained. So to measure this, they decided to set up a way to gauge what was happening. And in 1848, a post was set up near the mere to measure what may happen. This was installed at the lowest point in the area and also the country. So the post was pushed down 6.7 meters into the ground. The base was embedded in the clay and the top of the post was cut off with the soil surface. You couldn't see any of this post. And as anticipated, the mere was drained and the land quickly began to sink and the soil surface began to move down as the peat compacted, weathered and eroded. So over time, they took measurements and it shows immediately on drainage, a subsidence of around 23 centimetres a year was recorded for the first 30 years. It has started to slow down, but it's still reducing at around a centimetre a year. And today, approximately 4 metres of the post is now showing above ground level. It's a good record of the issues surrounding drainage in this area. Next slide, please. So positive story now. We've got Home Fen. This is a national nature reserve owned and managed by Natural England. It's located just south of Peterborough in Cambridge. And as I mentioned, it's near the post. It's one of the last remaining pieces of this ancient fenland with this peat profile. And it hosts the UK's lowest land point created by the shrinkage associated with this historic drainage. But the site has received a grant through DEFRA's Nature for Climate Fund for peatland restoration, and Natural England is working as part of the Fens East Peat Partnership alongside the Wildlife Trusts, National Trusts and the RSPB to restore peatland sites across Lincolnshire, Cambridgeshire, Norfolk and Suffolk, and has worked closely with the Environment Agency, IDBs, local authorities, farmers and fenland soils to bring this Home Fen project forward. So across Home Fen, restoration proposals have been developed to reroute the existing drainage and manage the water in a different way to hydrologically isolate the fen and maintain a higher water table, as re-wetting the peat is essential here to slow further degradation, reduce subsidence and improve the habitat. At Stantec, we created a detailed 1D, 2D hydrology model built with detailed channel conveyance information and key structure details for the existing drainage system to simulate baseline runs of the present drainage and also the post-restoration scenarios. We also assessed flood risk, as restoring a degraded peatland does require a careful and considered approach both on-site and off-site. This project forms part of the wider Great Fen project, which is a long-term initiative to restore a continuous area between Home Fen and Woodwalton Fen, and it forms one of the largest restoration projects of its type in Europe. So it's very exciting to see how this project will progress. Next slide, please. Just to touch on briefly is polluter or farming on rewetted peat. This is a system of agriculture for profitable production of wetland crops. In the context of lowland peat, it's most usually achieved through raising the water table to achieve wetland conditions to grow wetland crops. Government initiatives such as the Polluter Exploration Fund was set up in 2022, which looked to unlock barriers to making commercial polluter a reality. And 88 native UK wetland species were identified with promising potential. For example, we've got typha shown on the screen there, or bulrushes, which have long white fibres that could provide a sustainable and biodegradable solution for insulation or clothing. And more recently, we have the government's Environmental Improvement Plan 2025, which sets aside investment for restoration and polluter trials. However, commercial growing of these crops is at a very early stage, and we've still got many barriers to overcome on how to sow, grow and harvest these crops, as well as developing a good market for them. However, the opportunities are exciting and the potential environmental gains to be realised are not to be underestimated. To quickly mention as well is the Lowland Peat Water Discovery Grant from the Environment Agency, which I believe is currently open, which has around 4.5 million to help farmers and local partners explore more sustainable ways of managing water, considering land for peatland restoration and polluter. I think that's the end of the talk. So next slide, please. Yeah, thank you to all the attendees, BHS, Claire and Lisa, for having us. Do we have any questions?
Yes, we've had a few come in. Hopefully you can see in the Q&A published window a few that we've had in. Please do add in more if you think of any now. We will start with a question from Tim. So Tim Taylor asks, in your experience, what are the main challenges of convincing IDBs of option effectiveness in relation to uncertainties in hydrology and modelling, and how best to address this? Do you do more scenarios or sensitivity testing, or is it engineering assessment and judgment?
From my experience, as alluded to by Max, the experience of the IDB is quite valuable. So a lot of the times we're verifying their lived experience over a number of decades with what the model has shown us. So there's kind of an interrelationship between the two. And that usually it's both of those elements that inform optioneering and eventually a preferred solution. I don't know if that answers the question.
Yeah, I would also say, yeah, it's sensitivity testing various little changes to any assumptions and things like that, just to build up that evidence base of trying to show that the model is robust and it's been sense checked. Say, providing that justification, they're usually pretty happy with the outputs, provided they seem sensible to them as well, just like Sean said.
Great, thank you. And then I'll take the liberty of asking a question. So do you think there is much potential for natural flood management techniques in these types of catchments? And I ask this because the next round of FCRM funding includes specific parts dedicated to NFM measures, and it'd be interesting to see how, if and how they could be applied in pump catchments. What are your thoughts on that?
Happy to take that one if you want. Yvonne or Sean, do you want to go? Yeah. I think because they're such an engineered system, and obviously the water level is very heavily managed anyway, I think there's limited potential scope within the main parts of the catchment for natural flood management. There could be little, like smaller scale opportunities, potentially more related to the farmland or any fringe areas, or if there's upland areas that can drain into pumped or fenland catchments. I think there's more opportunities there for things like leaky dams to slow the flow and things like that. But because they're so engineered already, I think the scope's limited, but I wouldn't say it's zero. I think there's always something.
I think it can support the fundamental engineering requirements to some extent, but not fully replace. So the example, replacing a pumping station completely, like Wrangle, for example, but it can assist it. It can kind of feed into a better water balance solution, because obviously now with climate change, you've got irrigation issues in the summer. So some landowners are looking at options to even provide like a bypass drain where the pump can feed a wetland system rather than just all discharge into sea or to a main river. So there is a bit more consideration of that full year-round solution. And the other thing is, in some schemes like Benneker, we're looking at the EA are considering, retreated coastlines in certain areas as part of their coastal management plan. And in those situations, obviously, there's great opportunity for ecological betterment if we're creating new wetland systems and bringing back the shoreline further inland.
Great, thank you. We've got loads of questions coming in now, and I don't think we'll have time to answer them all, but I'm going to choose one that's more focused on the peatland. How about this question on paludiculture? So a question from Robert Brown. Commercialisation of paludiculture presumably requires the use of heavy machinery, and how compatible is that with wetland management? Yvonne, I don't know if you'd like to have a go at that one.
Okay, I'll preface this by saying I don't know a great deal about methods of harvesting crops, but I think you can use a system of bog maps to take machinery onto peatlands, and I think they're looking at not using like traditional heavy machinery to harvest the crops. So I think it's like a low pressure type of machinery to extract the crops that are being grown. But yes, I mean you would very much struggle to harvest on a bog peatland without considering the weight of the machinery you were to use. So there's all sorts of things that sort of need to shift to be able to accommodate paludiculture.
Thank you. Okay, and let's take one final question. Okay, we have a question from Suman that sort of covers all areas of the talk today, so we'll go with that one. Centuries of drainage have caused significant peat shrinkage and land subsidence. How do current drainage strategies balance keeping the agricultural land dry while preventing further soil oxidation and carbon loss? It's quite a tricky challenge, I imagine, but interested to hear if you have any thoughts on that.
Yeah, I think the main challenge is, in hindsight, a scheme like this wouldn't be delivered today. But now you've got the infrastructure that Max outlined within the Fens. I think in the Great Level kind of catchment area, and it's not really known as that today, there's a large majority of that which is valued at over 50 billion. So it's kind of a balance between, obviously, sustainability, economics is a part of it, but there's probably prioritization of certain areas which are more suitable for restoration than others. And, there's a lot of pioneering projects such as the, what's that scheme in the Norfolk Broads scheme, Yvonne, you know more about that than me, where we're looking at areas that are more suitable for peatland restoration and prioritising them. Because ultimately there is an economic study there, and you have to protect most of the residential properties that are already established now and key infrastructure links, things like that. So yeah, it's probably a prioritisation to get best value for money.
Yeah, and I agree. Just to add as well, I think it's an awareness of what's needed to create a successful peatland restoration site. You do need sufficient water all year to a certain level. So it's about knowing which sites are best for a scheme such as that, and which can be retained as agriculture.
Mm-hmm. Yeah, so trying to balance and against the restoration and the economic needs of the catchment.
Mm-hmm.
Thank you. We're at time now. I don't know if, Lisa, that's why you put your hand up potentially.
I was just going to say there's quite a few really interesting questions. So obviously, like you say, Claire, we've run out of time. So if we're able to access the list of people's emails for the people who've attended, then it'd be good for us to get a response from the speakers and offer that to those who we haven't been able to answer, so that everybody gets that. I think that'd be really useful. There's some really good questions, so it'd be good if we can.
Yeah, definitely. I think what I will try and do is put the answers to them in the comments under the YouTube video when we put the YouTube video up, and then you should be able to see them all. But yeah, I'd like to finish the event by thanking all of our speakers again for absolutely fascinating talk. It's one of my favourite topics. So thank you for agreeing to come along and talk about it today. And please do join us on the next BHS webinar. So thank you very much, everyone. Goodbye.
Thanks for having us here.
Thank you.
Thank you.
Bye.